So we've just stated the Gram-Schmidt algorithm. The Gram-Schmidt algorithm takes a basis for any vector space and produces two new bases of the same vector space. The first basis consists of vectors which we denote by W's, and those basis vectors are mutually orthogonal. And then by normalizing those W's, we produce the Q's, which give us an orthonormal basis of the vector space. So the question now is, well, how does that help us? Why is this a useful concept? And the answer is, this gives us QR factorizations. So we have a nice elegant theorem now that states we can use the Gram-Schmidt algorithm to factor any matrix as A equals Q times R. How do we get the matrix Q here? Well, we obtain the columns of the matrix Q by applying the Gram-Schmidt algorithm to the pivot columns of the original matrix A. Remember, the pivot columns always form a basis of the column space of A. So that is a basis of the column space. And then if we run that basis through the Gram-Schmidt algorithm, that will give us the columns of Q in a QR factorization. What about the matrix R? We can always get the matrix R by taking Q transpose that we just calculated, Q, and multiplying by the matrix A. And it turns out this will always be an upper triangular matrix. So this illustrates how the Gram-Schmidt algorithm gives us QR factorizations. So previously, we did an example of the Gram-Schmidt algorithm. We applied the Gram-Schmidt algorithm to the columns of this matrix on the left here, A. And we produced Q1, Q2, Q3, which I'm now putting into the columns of this matrix, and I'm calling it Q. So that's the Q in a QR factorization of A here, or an RQR factorization of A here. Where do we get the matrix R? Well, we can now find R by defining it as Q transpose times A. So here's Q transpose, and I'm multiplying by A. When I do the matrix multiplication here, that gives me my matrix R. And when I went through the multiplication, I got this upper triangular R. The first row is root 3, 2 root 3, negative 12 root 3. The second row is 0, 1, negative 10. And the third row is 0, 0, root 14. So that gives me my QR factorization. A is Q, and we got Q by applying the Gram-Schmidt algorithm to the columns of A. And then R is this upper triangular matrix, which is Q transpose times A. So we now have successfully calculated a QR factorization of A. And remember, once we have a QR factorization, life is simplified dramatically. I can now easily solve any projection problem onto the column space of A, because the projection matrix onto the column space of A is Q times Q transpose, which is not terribly difficult to calculate. And I can also simplify any least squares problem involving the matrix A by reducing the least squares equation, A transpose A x hat equals A transpose B, to R times x hat equals Q transpose times B. And that is a simplified version of the system because R is upper triangular. So for the first lesson this week, we discussed why A equals QR factorizations are so nice. And then in this lesson, we've learned how the Gram-Schmidt algorithm produces QR factorizations of a matrix.